very last thing we're going to look at is the idea of the mean free path. So this is sort of like the inverse of the collision rate. But instead of thinking about numbers of collisions happening, maybe we want to think how far can the particle go before it hits something else. And so that's what we call the mean free path. So this is distance traveled, and all of these are averages. Average distance traveled between collisions. And so again, we're going to assume that our particles, since we're talking about averages, that our particle is moving at the average speed, because we're thinking about an average particle, and we know the collision frequency ZA. That's the same thing that we just calculated in our previous videos. So if we think about this sort of from a units perspective, what we want to know is how many meters does something go per collision, in between each collision. So we can think about this as, the speed is in meters per second, our collision frequency is in collisions per second. Those seconds are just going to cancel out. So if we take the speed divided by the collision frequency, we'll get meters per collision. Which means we should just take U divided by ZA, and that is what we call L, the mean free path. So if we can calculate the average speed and the collision frequency, we can find the mean free path pretty straightforwardly. We can also simplify this, but change this a little bit by getting a specific value for ZA. Well, actually, let's go ahead and write out what ZA is. So average speed divided by rho times sigma times square root of 2 times average speed. That average speed is going to cancel out. And so this will just give us 1 over rho sigma times the square root of 2. So that's a perfectly fine mean free path. We can also find a value for rho. We showed in the previous example calculation that rho is equal to P times Avogadro's number over RT. And we can make that substitution to replace it, and then that gives us a version of L that's in terms of things that we usually measure. So RT over square root of 2, Avogadro's number, collision cross-section, times P. So these two equations are equivalent, but this is sort of the final version that we're going to look at. And so this is an example of, this is the calculation of the mean free path. And so again, very closely related to collision frequency. Now we can do the same calculation we just did, for the atmosphere, for nitrogen in the atmosphere. What is L? Well, we calculated the average speed was 475 meters per second. Well, we didn't actually calculate it, but I told you that's what it is. You can calculate it yourself and double check my work. And then we calculated ZA. We did put all the numbers into 7.35 times 10 to the 9 collisions per second. If we put those two numbers in, we get 6.47 times 10 to the minus 8 meters per collision, or about 65 nanometers. So compared to the size of a individual molecule, which is tenths of nanometers, it travels a pretty far distance, and that's why it's a gas, right? If it traveled much less than that, then things would start to condense, and then you'd have a liquid instead of a gas. And so we'll also look during class. We'll look at an example of doing this in a much different environment than the atmosphere. We'll look at space and see how these values look in space. But this is the conclusion of Chapter 27 on kinetic molecular theory.